All right, so hopefully you printed off some notes about how to solve exponential equations. I'm calling this continued because we did technically talk about this with application problems, but now we're going to look at them when they're a little bit out of context. So to start, it says work with a partner, but unfortunately we're at home, so you have to do it on your own. And what we're going to do is we're going to try to graph both the left and the right hand side and see which graph it matches up with. So for instance, I'm going to look at graph C right here to start. I think it's actually a little bit easier to work backwards. So graph C, this would be the line y equals 2, and this would be the graph of e to the x. And I know that because I go through those key points of 0, 1, over 1, up to 0.78. So it looks like graph C is going to go with A right here, and it wants us to figure out what the answer to this equation would be. So if e to the x is equal to 2, then the answer would be this purple dot right here where they cross over one another. Okay, so I'm going to look now at, let's look at graph B maybe. So graph B looks like it has this line right here that's equal to a half, and then it looks like we have this line here that's definitely some sort of a log graph, goes through the point 1, 0. And then if I were to extend this out, 2, 3, 4, 5, 1, so this is the graph of log base 5 of x. So I'm looking at e, and if I wanted to solve where does log 5 equal 1/2, I would again look at where these two things are crossing over, where the red and the blue come together. So what I'm going to do, I'm going to have you try graph A for just a second. I'll pause it so you can try graph A and figure out which one of these is graph A, and then I'll scroll down and I'll work on D through F in case you weren't able to print the notes. So go ahead and pause your video, see if you can figure out which one of these equations that are left is represented by graph A. All right, so hopefully you came up with graph C. And then our answer, where are these two things equal, is always going to be this little dot in purple that I'm drawing. So I'm going to move up these graphs. Oh, all my writing is still there. Better get rid of that. Move up these graphs, D, E, and F. I'm going to have you pause your video again and see if you can figure out which one of these represents each of these equations. And then remember, our answer to that equation, if we could solve it, would be where the red and the blue are crossing over. So pause and see if you can match up those last graphs. Pause now. Okay, so again, if we wanted to solve where these equations were equal, we'd look for the value of that purple dot. So this would be when x is about 1/2, or when x is about 4. But what we know from math is that there are more exact ways to solve that than relying on graphs or drawings. So we're going to work on solving exponential equations that have a variable in the exponent. All right, so method 1 is going to work sometimes. All right, so that's why we're going to do it first, but only works some of the time. Write each side of the exponential with the same base. So here we have in example A, we have a base of 3 and we have a base of 3. Well, if we have two things that have the same base, then whatever is up in their exponent, those two things must be equal to one another. Sorry. So we're going to solve this just like we would. I'm going to add 12 to the other side. Actually, no. We'll keep it this way. We'll keep negative 12 over here. I'm going to subtract 3x from both sides. So I'll get negative 2x equals negative 12. And then I'm going to divide both sides by negative 2. So x is equal to 6. And you can always check by subbing your value back in. Okay, well this one was pretty straightforward because 3 and 3 were exactly the same. But if I look here, this one has a base of 5 and this one has a base of 25. I can't get any simpler than a base of 5 in terms of powers, but I could rewrite 25 as 5 to the second. Okay, so 5 to the second to the x plus 1. Remember, when you have a power to a power, you're going to multiply. So this would be 5 to the 2 x minus 2, because I'm going to multiply up there, is equal to 5 to the x plus 2. Well, now I have a situation just like example A. And so whatever is up here, because they have the same base, will be equal to what's ever over here. Again, because they had the same base. So I'm going to add 2 to the other side. My pen stopped working. I'm going to try to add 2 to the other side. There we go. So I get x plus 4 is equal to 2x. So then I'm going to subtract x from both sides. And I would get that 4 is equal to x. And again, I could check my answer by subbing back into the original equation. All right, so method 2 will always work, but you have to make sure you know how to use your calculator. So if you don't have fancy calculator buttons, method 2 is not going to be that great for you, but we're still going to talk through it. So method 2 is use the logarithm with the same base as the exponential and apply properties of logs to isolate the variable. So we want to first get our exponential alone, just like when we did these story problems before. So I'm going to get my exponential alone by subtracting 1. And then it says use a logarithm with the same base as the exponential. Well, here my base is 3, so I'm going to take a log base 3 of both sides. So then use properties of logarithms to isolate the variables. So right now what I have is log base 3 of 3 to the x is equal to log base 3 of 28. But we know from our properties that I can swing that x right down in front. And log base 3 of 3 is going to cancel itself out because that value is just 1. So I get x equals log base 3 of 28. This is an okay final answer. You could also use your calculator and get a decimal answer. What I would ask you to think about right now is we started with 3 to the x equals 28. And I know that 3 to the third is 27. And 3 to the fourth is 81 from my power book, which means that hopefully, since we know 28 is somewhere in between there, it's going to be a value very close to 3. So I can check that in my calculator. Again, if you have the newer calculator, this will be pretty straightforward. You go to math, and then you can scroll up to log base. So I would take log base 3, right? 3 to what power gives you 28? And it's 3.033. But if you don't have the fancier calculator, you can just leave your answer right like this, and you could estimate it to be between 3 and 4. All right, this next one, I already have my exponential isolated. So I'm going to go ahead and take a log with the same base as the exponential. So in our case, this will be a log base 4. What I do on one side, I have to do to the other. Using those properties of logarithms, I can swing this whole x plus 6 down in front. And then I still have, I'm writing over my own Bitmoji, log base 4 of 4 equals log base 4 of 17. So log base 4 of 4 goes away. And then to get x all by itself, I'm going to subtract 6 from both sides. So I could write this as log base 4 of 17 minus 6 is equal to x. Okay, if you have the newer calculator, you can actually do log base 4 of 17, figure out what that is, and then subtract 6. If we were estimating 4 to what power gives us 17? Well, 4 to the power of 2 gives us 16, so it's probably something just greater than 2. So to check my calculator, into math, log base 4 of 17, yep, just greater than 2, and then minus 6. So I could get an answer of negative 3.956 if I wanted to. But leaving them with logarithms is actually okay, and it's a more exact answer than rounding with decimals. All right, method 3, 3 hearts. Method 3 is the one that I actually like the best because it's the method that will always work for you, okay? So it's good to recognize those other ones using properties and understanding the math number sense of it. But in terms of calculator usage, this is going to be your most efficient way. You just have to know your properties of logs. So this says no matter what the base is, use the natural logarithm and then apply those properties. So I have my exponential isolated. So I'm going to take the natural log of both sides. I'm going to swing the x down in front using my properties of logarithms. The natural log of e, because those match, that's just a number of 1, so it goes away. So x is equal to the natural log of 28. And that's it. And everybody has the natural log button on their calculator. So you could just type ln of 28. Okay? Now, in thinking about this, a nice little reminder, ln is a lowercase l and a lowercase n. Okay? No i's involved there. Make sure you're careful. No ones, that type of thing. Okay, so now this gets more interesting because we're going to use a natural logarithm for method 3, but I don't have anything with e over here. So you're probably like, Ms. Schwartz, what? How would that possibly happen? Well, that's just it. The natural logarithm is so powerful that you can just take the natural log of both sides. And let's see what happens. We get the natural log of 17 equals the natural log of 4 to the x plus 6. Just like the other one, I'm going to swing the x plus 6 down in front. Okay, but now this time the natural log of 4 will not go away like the natural log of e did. So now I want to just use what I know about solving. I want to get this x all by itself. And I've got this multiplication thing stuck here. So to undo multiplication, I'm just going to divide by the natural log of 4. So now what I have is the natural log of 17 divided by the natural log of 4 is equal to x plus 6. Still trying to get that x all by itself. I would then subtract 6 from both sides. So I get the natural log of 17 divided by the natural log of 4, all minus 6 is equal to x. And what's so nice about this is that everybody has an ln button on their calculator. So I can do the natural log of 17 divided by the natural log of 4 minus 6 is equal to that negative 3.956. Negative 3.956 is approximately equal to x. But this, again, would be a perfect answer because it's perfectly exact. Okay, so again, 3 methods. Method 3 will always work, and it's possible on every calculator to do method 3. So kind of keep that in mind for your own technology. But really what we're looking at, or what we're thinking about, is where does the graph of this guy cross the graph of this guy? Okay, so remember your goal is to isolate the variable. You're trying to get x by itself. I like to say you should make sure that it gets down safely from its heights. So an exponential always starts with some sort of base, and then you've got your x way up high. And so in order to get that x down, you've got to take some sort of a logarithm, either log base b that matches, and then you can write the x out in front. Or you could, instead of taking log base b, you could just take the natural log and swing that down. The only thing to be careful of there, remember, is whatever you do to one side, you have to do to the other. So we also did a lot of applications already where time t was up in the exponent. So remember we answered the question of when will this happen, when will this happen, when will this happen? We were always using logarithms to solve for t. These are very real things that you will want to understand as an adult. We talked at the end of the one video about applications that this actually describes the pandemic that's going on around us, is exponential growth. So just keep in mind when we're doing this. I know it's hard to learn remotely, but we are getting there. We are taking our time. We're around if you have questions, and all of this stuff, more so than ever really in math class, is very real in our real lives. All right, there are 5 questions on big ideas that you could do to go practice your skills and try methods 1, 2, or 3, whichever one you prefer. Sometimes one is easier than the other, but method 3 will always work. All right, see you later.